Chapter 2, Functions and their Graphs. Section 2.8, Combining Functions. Just as we can combine numbers under various operations, addition, subtraction, multiplication, division, we can do the same sorts of things with functions themselves. So we begin with the four basic arithmetic operations applied to functions. Let f and g be functions with overlapping domains. Then for all x common to both domains, the sum, difference, product, and quotient of f and g are defined as follows. As you'll see with these definitions, the operations are defined the way we would expect them to be defined. So the sum of f and g, f plus g of x, is f of x plus g of x for all x in the domain common to f and g. The difference of f and g, f minus g of x, is f of x minus g of x. The product of f and g, f times g of x, is f of x times g of x. And the quotient of f and g, f over g of x, is equal to f of x over g of x, with the additional provision that x be chosen such that g of x is not equal to 0. Let's apply the definitions described above to two functions given in example 1. F of x equals x squared minus 4, g of x equals x plus 2. Find the sum, difference, product, and quotient of f and g, simplifying where possible. We'll find that this is quite straightforward. So first of all, the sum of f and g, f plus g of x, is defined to be f of x plus g of x. F of x is x squared minus 4. G of x is x plus 2. And then simplifying, we could write x squared plus x minus 2. So the sum of f and g is a new function, a function in its own right, the function x squared plus x minus 2. Okay, the difference would be f minus g of x, defined as f of x minus g of x. Okay, and again, f of x is x squared minus 4. G of x is x plus 2. That has to be subtracted, so we want to use parentheses there. That is x squared minus 4 minus x minus 2, and that leads to x squared minus x minus 6. The product of f and g would be f g of x, f times g of x, which is defined as f of x times g of x. Again, f of x is x squared minus 4. G of x is x plus 2. And then multiplying, we can apply FOIL. The product of the first terms is x squared times x, which is x cubed. The product of the outer terms is 2 times x squared. The product of the inner terms is negative 4 times x. The product of the last terms is minus 8, negative 4 times 2. Since these are four unlike terms, we would just leave the answer in this form. And finally, f over g of x is defined as f of x over g of x. F of x is x squared minus 4. G of x is x plus 2. Now we could leave it in this form, but we could also simplify it because x squared minus 4 is a difference of squares. It's x minus 2 times x plus 2 divided by x plus 2. We have a common factor of x plus 2, so that gives us x minus 2. Now, having done this, we should also note that the quotient is undefined when x is negative 2, because x plus 2 is in the denominator and cannot equal 0. So even though the quotient simplifies to something that is basically a non-quotient, x minus 2, we still must restrict the domain to values of x not equal to negative 2. So when we simplify, we kind of lose that restriction. But that restriction has to be there because x minus 2 was initially formed by performing a division. And when we do the division, we cannot divide by 0, which would occur if x were equal to negative 2. Essentially, the function f over g is its graph is a straight line. It's a linear function, with the exception of at x equals negative 2, where there's basically a hole in the graph. So the graph of f over g would be a straight line with a hole at x equals negative 2. Now looking at example 2, for the functions f and g of example 1, find two ways to compute f plus g of 4. Recall that in example 1, f of x is x squared minus 4. G of x is x plus 2. Now obviously, one way that we could compute f plus g of 4 would be to simply use our result from example 1. We found the function f plus g of x, and that function was x squared plus x minus 2. So what we could do then is simply substitute 4 for x and compute the function value. So that would be 16 plus 4 minus 2, which gives us 18. So one way to compute f plus g of 4 is to add f of x and g of x, find the function f plus g of x, and then substitute 4 into that function. There is another way we could do it, however. A second approach would be to say that f plus g of 4 is f of 4 plus g of 4. If f plus g of x is equal to f of x plus g of x for all x in the domain common to f and g, then it follows that for the specific value of x, x equal to 4, f plus g of 4 equals f of 4 plus g of 4. Now we can compute f of 4 and g of 4 individually using the individual functions f of x and g of x as shown on the left there. Let me just compute those values below. F of 4 would be 4 squared minus 4, x squared minus 4, which is 16 minus 4, or 12. G of 4 would be, g of x is x plus 2, so that'd be 4 plus 2 is 6. Therefore, f plus g of 4 is f of 4, which is 12, plus g of 4, which is 6, and 12 plus 6 gives us the same result that we obtained before. So in other words, we can compute f plus g of 4 by first finding f plus g of x in general for any x, and then substituting 4 into the sum function that we obtained with f and g. Or we can compute f plus g of 4 as f of 4 plus g of 4 using the functions f and g individually. So it's actually not necessary to combine f and g for all x to compute f plus g of a specific value of x. Another method of combining functions is via function composition. This is perhaps a more important method of combining functions than what we've described earlier. Here's the definition. Given functions f and g, the composition of f with g, denoted it looks like fog, but we usually just read it f composed with g, f composed with g. The circle is the operation symbol for function composition, just as we would say use a plus sign for addition. This is just the symbol used for function composition. So the composition of f with g is the function defined as follows. F composed with g of x is f of g of x. The function f composed with g can also be referred to as a composite function. The domain of f composed with g is a set of all x in the domain of g such that g of x is in the domain of f. So for a value of x to be in the domain of the composition of f with g, first of all, x must be in the domain of g, and then whatever the value of g of x is, that must be in the domain of f. So there's really a two-step process to determining the domain of the composite function. And I'll illustrate that in the example below. Although function composition produces a single function, it's still important to understand its operation as a two-step process, especially for the purposes of determining the domain. This process actually occurs in reverse compared to how the notation is written. That is, f composed with g must be understood as first g, then f. And there's a diagram below to illustrate what we mean. When we compute f composed with g of a particular x, that x first gets substituted into the function g to produce g of x. Then the g of x gets plugged into the function f to produce f of g of x. So plugging x into g and then plugging g of x into f, this two-step process is essentially the how we understand the function f composed with g. So in other words, f composed with g is one function, but it's understood in terms of a two-step process. First plug into g, then plug into f. This will hopefully become easier to understand when we look at some examples. I'd like to conclude this video by just mentioning that the fact that function composition actually occurs in an order that is the reverse of the way the notation is written, this is basically a consequence of how we use function notation in the first place. If you think about f of x, let's say a particular function value f of 4, what do we do first, or how do we think about it? We actually think about taking 4 and plugging it into f. I mean, that's actually how it works. We first observe the x, and then we look at how the function is defined, and we plug that x into the function. So actually the way you operate with a function is really in reverse order from the way that it's written. We first see f and then we see the 4, but actually we start with a 4 and we plug that into f. And that idea is underlying why when we write the function composition we see things in the reverse order.